Hello and welcome to the second video on introduction to control systems. In this video, I will first demonstrate controller in action, see that it works, how it's implemented, and then move on to some basic mathematics that is necessary whenever we are designing any control systems. Okay, so let's recap what we saw. So, see, this is our main objective in this video series, or in of any control system. You have a system, you want to make sure that its output matches a given reference value, and you don't have much control over the disturbance, you don't have much control over the system, maybe some control over how you design your system, but once it's there, you don't have much control over the system itself. The only thing is you can change the input you're giving to the system in order to control this output. And the way you do this is you put a box here, so we call a controller. And what this controller needs to do is it needs to measure the error, calculate the error. The error is defined as the difference between the reference and the output, the reference minus output. If error is positive, then increase the input, and if error is negative, then decrease the input. And this is the system that in total we are trying to simulate. This is the motor for which we saw the differential equations and everything here. This is the motor along with some drivers here. So this is our system, or you can refer it to as the plant. This is the controller. So the controller goes inside the microcontroller in form of a software. So the integrator, or however you are changing the reference, calculating the error and changing the reference and everything that happens in software inside the microcontroller. There are ways to do it using analog circuits as well, but in this video I'll be implementing it in Atmega in software, because most likely 90% of the cases it's implemented that way. And this here is our output. The way we are measuring it is via rotary encoder. This is the speed, the output of the system, and here we are giving the input where the microcontroller is connected to the drivers. How we are giving the output and how we are measuring the input, I'll describe in more detail in some next videos. Okay, so the controller, as I mentioned earlier, it's implemented in software inside a microcontroller. It can be in some other language like Python, but most likely a microcontroller is kind of memory and space sensitive. It doesn't have much space like your normal CPU, so it's most likely in most of the cases implemented in C or at max in C++. And this is the controller for this particular system. And this is a small C code. I'll again explain this C code line by line in the later few videos, but just keep a note of this for now. So let's run the simulation with feedback controller implemented and one simulation without the feedback controller implemented, and see what is the results that we get. This is my Python script which uses the testsim as a library and the CLI commands library and nodes, and this is my two motors. One is running in open loop, I'm giving it a constant voltage input, and the other one is connected to the microcontroller and it's giving off feedback. Okay, so right now I'll just make these two torques as 0 and see what my output is. Simulate this. So now we have our outputs. So you can see without any external torque or disturbance, both of them settle at around 100 radians per second of speed. Let's see, our main objective was that even with the torque, the feedback, this blue one, should settle at 100 eventually. So let's see if that works. So now I'll just uncomment these two lines. That means I'm giving them some torque. So same torque on both the motors. And now let's compare the output that we have. Okay, just run the same script again. Okay, so in this case you can see without in the open loop, or open loop effectively means that I'm still giving the same input and the output of the motor has dropped. And in this case, when I have a feedback in presence, it actually applies that feedback, and it eventually settles down at 100 radians per second. Transiently, initially there is some disturbance here because it somewhat drops and then rises up. So there will be some disturbance, there might be some disturbance, but eventually it settles down to back to the reference speed. Now I will be discussing some mathematics that we'll be using to design the control systems, and that mathematics actually helps us to understand how much is this peak going to be. So here you see there is no peak, it just comes up and settles down here. So in the mathematics we'll see how to control this peak, how can we bring it down or go up, how many oscillations are going to be there, and to kind of analyze our controller if it's introducing any oscillations, or in the worst possible scenario it's just blowing up the system entirely, making it completely unstable. So that is also possible. So in order to prevent that and to kind of make sure that this overshoots and everything are under control, we'll be developing some mathematics. I'll be reviewing some mathematics going ahead. So this mathematics starts with Laplace transform. A Laplace transform you can simply define using this equation. So if you have any function transform from a function of t or time to some function of s. So s is kind of a vague complex number which we can define as sigma plus j omega, and if you put sigma here, this equation transform into the equation for Fourier transform, and your j omega is the frequency, and this is the Fourier transform. If you don't know, Fourier transform is the representation of this function in the frequency domain. So this is how we use it, and there are some useful properties of Laplace transforms. You can easily prove it from the equation that we had earlier. It's simply that if you have a derivative, you just multiply s to the Laplace transform, and the Laplace transform of the nth derivative is to multiply s raised to the power n to the Laplace transform. There are a lot of other properties, you can look up them anywhere, but right now I'll be using just these two mainly. So I'm just putting a focus on these two. So what is the Laplace transform of our motor system? So in a first order approximation, this was a differential equation for the speed and the input voltage, and this we can simply write it as C. This is the first order equation, and if we take Laplace transform on both sides, the constant remains the constant. You can just put it out. This derivative you can multiply it by s. This omega is simply an Laplace transform of omega, and this is the input. You can rearrange it to make it look like this, and or something like this. So what we have here is a direct function from the input voltage to the output speed, and this is what we call as the transfer function or the plant transfer function. In most of the textbooks that if you ever see on control systems, this is the transfer function is effectively the Laplace transform of the ratio of the ratio of Laplace transforms of output and input. So weird way to put it, but like this is how it's done. So why are we doing all this? Why do we need a Laplace transform? Is to basically ease out our representation. So if we have a simple block here, I can just call this block a motor transfer function. What we are giving it is an input voltage, and what we are getting is an output, and the output we can simply represent it like this. Like this is the very definition. So one reason is now we can represent instead of solving a differential equation, you can represent your output as a function of input, just simply multiplying it from the with the plant transfer function. And this is one reason why we use the frequency domain analysis or the Laplace transforms, because that makes our mathematics and the representation, instead of writing a differential equation or something, you can just simply put a block diagram here to represent my system. And this is the reason that we use the Laplace transforms. So again, as I said, in the Laplace transform, if I put s equals to j omega, I get my frequency domain. This is the Fourier transform, and I'm in the frequency domain here. Now at very low frequencies, if my c omega is much smaller than k, I can neglect it, and my transfer function is simply 1 by k. And this phase, so it's a complex number, it will have a magnitude and a phase. And in this case it's almost a real number, so its phase will be almost 0. And if it's a much larger, then I can neglect this k, and in this case my phase will be minus pi by 2. So this analysis, and if you plot this transfer function, the magnitude as well as the phase, then that is what we call a Bode plot. So here now we'll be seeing some asymptotic approximations of the Bode plot. This is a transfer function, and let's just call this constant as k by c as omega 0. And if my frequency omega is much smaller than omega 0, then I can make this approximation we saw in the earlier slide. You can simply represent it as 1 by k. So this is my line here representing it, and in this case the phase is 0. And if my frequency is much larger, in that case I can represent it like this. And here if you take the magnitude and the log on the both sides, you see the log, the relation between the log of magnitude and the log of frequency is linear. So now I can simply represent it with a straight line like this, and the phase is a constant at minus pi by 2. So our plot looks something like this. So in the middle, so it's not possible to make such approximation when the frequency is around omega naught. And so in the asymptotic, or since this is an asymptotically approximate plot, we simply connect everything via straight line. So in this case here we just bring it up to omega 0 and connect like this, and in this case just put a straight line here. So yeah, and this is what we call a asymptotic Bode plot. Now let's compare it with an actual Bode plot. You can simply use the Python control system library we'll be using to make plot the actual Bode plot and compare it with this. This is my Python script to plot the Bode plot. This I have the motor parameters here. I'm calculating the k and c here, and the omega 0 in this case I can write it like this. I just plot the transfer function. I give a frequency range in the log space, and I plot my transfer functions here. So in order to plot this, I can simply, this is the name of my file, and I get the Bode plots. So if I compare it with the actual plots, the asymptotic plots and the actual plots, you can see here it's at very low frequencies it's at 0, and at very high frequencies it's at minus pi by 2, and in this case since it's in degrees it's at minus 90 degrees. Here it's a constant, almost constant at low frequencies, and at high frequencies the magnitude is, it's almost like a straight line on the log scale. Here around the place where it changes, it's not a very good approximation, so here it does not actually match it very well, but still on a log asymptotically it's a pretty good approximation for us. So we can use this to, we will be later be using the Bode plots to analyze how the system's response will be. Okay, so now let's move on. Okay. So now what I'll be doing is I'll be using the same Python script and actually running the motor with frequencies of different sinusoids, and just see how my response is, just to get a feel of that the Bode plot is actually representing some things in the physical world. My script here, so I have this motor and I'm just giving it a sinusoid of, say, to start with, let me just give a 10 hertz first. Okay, the motor parameters and everything are the same, and I'll just see. So at node 2 I'll be giving, this one is labeled as motor output, yeah, and this is my input, that the direct sinusoid that I'm applying. The sinusoid has a magnitude of 1. Okay, so now this motor sinusoid is the name. So now if I run Python motor sinusoid, okay, so I need to add this path to my paths first. I had to make some changes in my environment to be able to simulate this. Those are done now, so now this should run, and let's wait for its response. I have a very low, see this, it's not labeled for some reason, but whatever. So this, my blue is my motor speed and the green is my output. So right now it's like pretty high and it's almost in phase, so the phase is somewhat different, but like not like 90 degrees of difference. There's some similarity in the phase as well. Now if I increase my frequency to say 100, now let's see my response. Now I get, like, you know, this motor speed has dropped, it's not 30, and the phase has also, you can see it's roughly, you know, going around 90 degrees. And if I drop it for increase my frequency further, oh, it's a very high frequency, but now you can see my motor's magnitude, the speed's magnitude has dropped even below, and the phase is roughly, when this is at top, you can see this is at around 0. So the phase is also roughly around 90 minus 90 degrees. So the Bode plot again represents how if you give an input sinusoid of that frequency, what will be the magnitude and phase of the output of your system at that frequency. So Bode plot represents that is what the magnitude and phase are, their physical magnitude and phase of your system. We'll be seeing later how you can use this to analyze your peak overload, stability and everything. But for now, let's stop here and move ahead. So now we saw earlier that, is it recording? Yeah, it's recording. Okay, so we saw earlier that our controller is in most cases an integrator, and we want to include that in our system. So we want to take its Laplace transform so you can analyze it along with the system and see what the response is. So in the time domain, integrator is something like this. I have an output, I just integrate over the input and get it. So that means I can differentiate on both sides to get, you know, differential of the output is my input, and if I take a Laplace transform on both the sides, I can make a transfer function of my integrator as 1 by s. That is simply what it is. So the block diagram of the system with feedback will be like this. You have my plant here, the system, the reference here, the output here, and taking the difference. The ki is a gain for the integrator that we can control. This is my integrator block, and this is my input, and this is my plant. So if you just write equations for it, you can rearrange this equation, and this is your speed to my reference transfer function. So if I give suddenly a reference of some value, this is what my output speed is going to be. And in the next lecture, we'll be seeing that this actually settles down at whatever my reference value it is as time goes to infinity. And in the next video, I'll also be seeing what the integrator gain and other system parameters have and their effect in the transient response of the system. And I'll be going into some detail with respect to what the simulations setup is. Setup means the Python script that I have, how it works, how the encoder and everything else in the system works. And yeah, that's pretty much it for this video. Thank you and have a nice day.